Hello students, welcome back. Let us resume our discussion in section 6, Euclidean Algorithm. Here's the statement. In a division algorithm, the greatest common divisor of the starting pair, the dividend and the divisor, is equal to the greatest common divisor of the dividend and the remainder. And remainder being smaller, we got something smaller. Quotient does not contribute yet. We went through a couple of example problems. Here we go. 662, that's bigger of the two. Yeah, it's going to be a bit easier if you look at it this way. And then divide by 414, and we end up with the remainder 248. That means, yeah, we got to here. 414 and 248. Do it again, and we get remainder 666. So 248, 166. And then do it again, another division algorithm, 166 and 82. Another division algorithm, we get 82 and 2, that's it. 2 divides 82, so we have the GCD. We went through this kind of computation. Remember? Here's another example problem. Here's the first division, and then we get 693 and 189. And another division, and then we get 189 the divisor and 126 the remainder. Got up to here. Another division, 126 and 63, got up to here. And another division, it turns out 63 divides 126, so that's our GCD. Oh, good. And of course, there are more problems. So that kind of thing is Euclidean algorithm. Basically, we start from a big number A and another big number B, but let's rename all those into R0, and then let's say this was R1, and then by division algorithm, I get R2, and another division algorithm, we get R3, and so on and so forth. And eventually we get 0, the divisibility. Now this one here is the GCD. That's how we got the Euclidean algorithm done. But of course, we didn't prove this. That's what we're going to do now. We went through a couple of example problems, how the reduction is formed. We went through those. We didn't prove it. Let's prove it. Ready? Here we go. First, here's the setup. D0 is the GCD of A and B, the original, and D1 is GCD of B and R, a reduced version. We'll prove these two are the same. After all, this one left-hand side is D0, and this one is D1. How are you going to prove it? Well, both are non-negative, so we're going to prove that D0 divides D1, and D1 divides D0. That's what you're going to do. Very, very typical thing when you have to show two things are equal to each other in number theory. Remember, in analysis, how did you prove two things are equal? One is less than or equal, and again, greater than equal. You use two inequalities, remember? When you had sets, then we had one subset and then superset. But in number theory, very typically, we use the divisibility, one direction and the other direction. It works for non-negative numbers. Okay, so we have this one and that one to show. The first step, D0 divides D1. Oops, sorry about that. D0 divides D1. How do you prove the first? Directly from the definition, D0 divides B is a common divisor. So it divides A and it divides B, so okay, all right. Now, does it divide R as well? That's what we want to. Well, R is A minus BQ if I flip this BQ over to the other side. And B is divisible by D0, so that's 0 modulo D0. And A is divisible, so in the end we get 0 modulo D0. That means R is divisible by D0. Now, if you don't like this kind of mod computation, you can write like this: A minus BQ, and then A is some D0 sum times a certain number, and I'm running out of number. And then B is D0 times another number times Q. So this is D0 times some integer. You can do it like this if you want to, but you have to introduce many numbers, and it's hard to track those down. It's going to be a bit easier if you make yourself comfortable with mod operation. Not real mod operation, no, not yet. Just congruence to 0 only. Alright, divisible by 0, so equivalent to 0. Divisible by D0, so equivalent to 0. So eventually equivalent to 0. Equivalence or congruence, they mean the same thing, modulo D0. Anyway, what did you accomplish? D0 divides B, yes, B. And by this argument, D0 divides R. So it's a common divisor. So it must divide the greatest common divisor. Remember, common divisor divides the greatest common divisor. And that's actually the same as D0 dividing D1. After all, this one is D1. Okay, all right. One done. Let's go the other way. This time, D1 should divide D0, and D1 already divides B because it's a common divisor, so B. So what we have to do is it divides A as well. See? It already divides B, and what we want to do is to prove D1 divides A. Well, let's go back to the division algorithm. Divides B, so this is congruent to 0. And then R, well, D1 is a common divisor, so it divides R as well. So B and R, they both divide both of them, so that's congruent to 0. So 0 plus 0, we get that. Another way to write the same thing is to do it this way. B times Q plus R, and then this B is some D1 times some number S1 plus, and then this R is D1 times something, and then consequently we get D1 times an integer. You can use this kind of proof too if you want to. This way you can avoid this congruent to 0 modulo D1. But if you follow this, then you have to introduce many new integers. So it's really hard to track down. It's going to be much easier if you make yourself comfortable with congruent mod 0. Congruent to 0 modulo whatever. In this case, modulo D1. Not modulo 0, excuse me, I said it wrong. Congruent to 0 modulo something. So in this case, B is divisible by D1, so it's 0. 0 times something is 0. R is divisible by D1, so it's 0. 0 plus 0 is 0. You have congruence to 0, so A is divisible by D1. Anyway, What comes after that? D1 divides B and D1 divides, oh, sorry about that typo. I'll correct it. D1 divides A. Divides both these two. Consequently, D1 must divide the greatest common divisor. And consequently, D1 divide D0. After all, this thing is D0. So we got both. D0 divides D1 and D1 divides D0. Both are non-negative, so they must be the same. Alright, this one and that one are the same. And remember the setup. R is smaller, so we got up to here. A, smaller, smaller. And then from here, apply this Euclidean algorithm once again. Then you're going to get R1, maybe R3. Yeah, R0, R1, okay. No, R1. And then do it again, R2. Do it again, R3. And so on and so forth. Eventually, you're going to go to 0. We have divisibility. So the one before that, that's how you can find out the GCD. And we went through a couple of examples already. Okay, that's a proof of Euclidean algorithm. And remember, we went through a couple of exercises already. How to find GCD through Euclidean algorithm. Let me show you those. Like this. And then another example here. Like that. Can I squeeze those into the same viewing window? No, I guess I can't do that. So repeated application of division algorithm. Quotient do not contribute. Divisor and remainder, divisor and remainder, divisor and remainder, and get down, down, down. That's how you can find the greatest common divisor. Okay, so much for the second 1/3 of section 6. First, we went through some example problems to find out the GCD using Euclidean algorithm. Second, this one, we just proved the Euclidean algorithm. Now, the third one, the next video, we'll have another application. And this time, we're going to apply it to Bezout's linear combination. Stay tuned. See you soon.